Hello, welcome back, everyone. The topic for today's talk is on glass breakage patterns. There have been a lot of advances in glass science and technology over the decades that have led to high-strength glasses, such as the Corning Gorilla Glass that is used in your phone, the laminated glasses that are on your car windshields, thermally tempered glasses that are used across a lot of architecture. However, despite all of these advances, glass still breaks, and it can break into different patterns. And what I want to do today is to give you an introduction to some of these glass breakage patterns and explain why they occur and explain how you can tell a lot about how glass broke based on these breakage patterns. So let's dive into it. First of all, the three main types of glass breakage patterns that I would like to cover today are for annealed, laminated, and tempered glasses. Annealed glass on the left tends to break following this type of starburst pattern, where you have cracks that are coming out radially from some central origin area where the impact happened. And you'll note that there's nothing to keep these shards of glass in place. So after the glass breaks, the shards will tend to fall down, and you'll be left with these very jagged pieces of glass, which can pose a danger if you're not careful. Now with laminated glass, we have three layers. These are usually two glass layers with a polymer layer in the middle that adheres very strongly to the two glass layers. And as a result of that strong adhesion, when a laminated glass breaks, you don't have the pieces flying out. Instead, they are stuck to the polymer. And what you get is you can see exactly where the pieces are, but you'll also have new cracks that pop in over time, and that's what leads to this type of spider web pattern as opposed to the starburst pattern for annealed glasses. And then finally, on the right, a very different type of fracture pattern occurs in tempered glasses. This is called dicing. It's also called frangibility. And what this means is that the glass is breaking into many small pieces because of the release of stored tensile energy contained within the tempered glass. So let us start with annealed glass. Now, most of the windows in your homes and office buildings are made from annealed glass. Likewise, most of the glass bottles, jars, glass tableware are also annealed glass. So most of the glass that is on the market today goes through an annealing process. The way this works is that the glass is formed into whatever shape that it takes on, either flat glass for a window or a bottle shape for a glass bottle or a jar, and so on. But that glass product could have experienced differential cooling as a result of being shaped in that form. In other words, the exterior part of the glass could have cooled faster compared to the interior part, which could lead to the development of stresses that are retained in that glass product after it has been formed. Now, if those stresses are not carefully controlled, they can lead to the glass product being weak or having weak points in it where it is easily broken. This is true also in art glass. It's very important for glass artists to anneal their work to make sure that it's not going to inadvertently break or undergo some sort of a spontaneous breakage process. The annealing process involves taking those pieces of glass art or whatever glass product it is that you're making and heat treating it at its annealing point, otherwise known as its glass transition temperature. This is kind of the boundary between where the glass has more liquid-like properties, more like a supercooled liquid, versus more solid-like elastic types of properties. So annealing takes place right at the boundary between those two. And the glass is held there for tens of minutes, all the way through hours. For large glass pieces, the annealing could even go on for months. For example, there's this the glass telescope here that was on the cover of our book, Fundamentals of Inorganic Glasses. This image this is actually coming from the Corning Museum of Glass of the first failed attempt at annealing this enormous piece of glass that ended up cracking, and they had to start over again from scratch to do it for an even longer period of time to prevent cracking. And so the annealing process can take any amount of time based on the thickness of the glass in question. Thinner glasses happens a lot faster. Thicker glasses require longer annealing times. But the end result is to eliminate any residual stresses in the glass. And so when an annealed glass breaks, what this means is that the breakage pattern is not the result of any internally stored stresses because all of those stresses have been eliminated. Rather, the breakage pattern that we observe in annealed glasses is a result of the externally applied energy from whatever object was coming into the glass to break it. So, for example, if this is a glass window, and if somebody threw, say, a rock or a baseball at this glass window, the harder that they throw it, the greater amount of energy that the stone or the baseball has when it encounters the glass. Now, the initial response of a glass to some externally applied mechanical stress is going to be an elastic response. So initially, something is just going to bounce off of it. The glass it'll deform a little bit and then it'll bounce back and go back to its original dimension. So that is the elastic response. However, when the stress becomes so large that we go beyond the elastic limit for the glass, glass does not have many plastic deformation modes, not like a polymer or many metals. Glass is unable to deform plastically to any significant degree. So when glass goes beyond that elastic limit, it needs to release that energy in some other way. And the way the glass does that is by breaking. It's by creating these new fracture surfaces, by breaking apart the bonds that are holding the glass together and forming these new fracture surfaces where each of these cracks exist. And that's the way of transforming the kinetic energy of this incoming baseball or rock, transforming that into surface energy by forming cracks. And so if you have a baseball that is thrown at a much higher velocity, that means that there's a greater amount of energy. And in order to dissipate that energy, there must be a greater number of cracks that form. Now, all of these cracks are kind of emanating out from this origin here. You can see it's very obvious where the initial impact occurred right here at the center, and all these cracks are emanating out radially, giving this type of starburst pattern. So this is something that is typically observed in annealed glasses because all that energy is coming from an external source. It's coming from whatever projectile is being thrown into the glass, and that creates all of these new fracture surfaces starting at this point of impact. Now, if we go to laminated glass, this shows an example of a laminated glass windshield. All windshields in automobiles are laminated glass, and this is for safety reasons. A couple of the things that you'll note here is that the glass, even though it's broken, it doesn't have pieces of glass flying out. And this is because the lamination involves taking two pieces of glass here on either side and then having an interlayer that is made from a polymer, which is usually PVBs, polyvinyl butyrol. This is a very sticky type of polymer, and it has a very strong adhesion to the glass layers. And there are a number of advantages to using laminated glass based on the distribution of the stresses. Having a thicker overall laminate provides greater strength compared to just a single sheet of glass. But very importantly, when we have a laminated glass, because of that strong adhesion between the glass and the polymer, when the glass does break, it doesn't have pieces that are being ejected. And so if a driver here is in an accident, it's really important that they be safe from any type of glass shards that get thrown out. Now, here you can see that there are at least 3 points where fractures occur. This poor windshield has seen better days, I'm sure. But here's an origin on the left, a really bad one in the middle, and another one here on the right. They're all quite bad, actually. But in any case, all of these fragments of the glass are held together for the safety of the driver. The other thing is that even though laminated glass can be made either from annealed or from tempered glass sheets for windshields, it's important to use annealed glass because when it breaks, it's important that the driver still be able to see through the windshield. And if a tempered glass were to be used, it would dice into so many small pieces that the driver wouldn't be able to see through it anymore. If the driver is in an accident, they need to be able to safely pull over to the side of the road. And that is, best done if it is two pieces of annealed glass with this polymer interlayer. Now, the final thing to note with the fracture patterns that can occur in laminated glasses is because these pieces are held together over a long period of time, and because there's a lot of new damage that is introduced during the fracture process, and including more stresses that may be generated during that process locally. All of this damage becomes additional weak points for new cracks to pop in. And so you can have pop in of new cracks that kind of go around this initial starburst pattern, and then you have new cracks connecting all of these radially emanating cracks, and that's what can give the spider web type of pattern to breakage in laminated glasses. Now, moving on, the next type of breakage pattern that is common to be seen is this type of dicing behavior that occurs in tempered glasses. When a tempered glass breaks, it breaks into many small pieces. And this is a result of stored tensile energy that is in the interior of tempered glasses. Now, there are two different classes of tempered glass. There is thermally tempered glass, which is made by rapidly quenching a glass from its liquid state into the glassy state. When that occurs, the outer surfaces of the glass undergo the glass transition and become more solid-like at an earlier time compared to the interior of the glass, which is still at a higher temperature. As a result, the interior wants to continue to contract as it cools, but the outer surfaces are already rigid. And so the interior is actually pulling on the exterior surfaces to pull them into compression. And all of that compressive stress in the outside parts of the glass needs to be balanced by an equivalent integrated amount of tensile stress. With chemically strengthened glass, this also involves installing compressive stress in the outer surfaces, but this is through a chemical means, through an ion exchange process. This is, for example, how Corning Gorilla Glass works. The glass is initially formed by having a small alkali ion in it, like sodium. That gets submerged in a molten salt bath that contains a larger alkali ion, like potassium. There is an ion exchange process that occurs where the smaller sodium leaves the glass and is replaced by a larger potassium. That potassium wants to expand the outer surfaces of the glass, but it's not allowed to since it's bonded to the interior of the glass. And so as a result, the outer surfaces are pulled into compression, and that compressive stress has to be balanced by a tensile stress in the interior. So these are just two different pathways to develop stress profiles as shown here. This particular figure is for chemically strengthened glass. You can see that there are high degrees of compressive stress at either surface. That compressive stress decays. It undergoes a zero crossing point of stress. This is called the depth of layer or depth of compression. And if you integrate all of this compressive stress at either surface, there has to be an equivalent integrated amount of tensile stress in the interior, and this is to satisfy the force balance condition. Now, the great thing about tempered glass is that this compressive stress layer provides additional protection against breakage. So if you want to break a tempered glass, you have to overcome not only the intrinsic strength of the glass itself, but this additional compressive stress as well. And tempered glass is safe from breakage as long as cracks are shallow enough that they don't penetrate through the compressive stress layer. So if a crack is short enough that it stays within this green region, within this compressive region, then you're safe because the compressive stress wants to kind of hold the glass together. However, if the crack propagates and it's long enough that it goes through this depth of layer, through this zero crossing point of the stress, then the crack tip would go into this tensile regime. And tensile energy is the type of energy that wants to, tear that glass apart. These are tensile forces that will want to pull the glass apart. And so when a crack penetrates into that tensile region, that's when the tempered glass will break. And when tempered glass breaks, it can do so in a fairly catastrophic fashion, resulting in many small pieces as shown here. Now, the reason that this happens is that all of that tensile energy that gets released acts to accelerate the propagation of the crack tip. And if there's a greater amount of tensile energy that gets released, which would come from having a greater amount of compressive stress, and that requires that balancing by the tensile stresses, that greater amount of tensile energy translates into a greater degree of acceleration, which means that the crack tip is going to accelerate more rapidly and reach its terminal velocity sooner. The terminal velocity of a crack tip in a typical silicate glass is about 2,000 meters per second, and this is governed by the speed of sound in the glass. And so when the crack tip reaches its terminal velocity of about 2,000 meters per second, it cannot release that tensile energy at a faster rate because it cannot propagate any faster. Now, the glass still wants to be able to release this stored tensile energy at a faster rate, but if the crack is unable to propagate any faster, the only option that it has is for that one crack to bifurcate, in other words, to branch into two new cracks where that process repeats itself. So, for example, this shows breakage of a chemically tempered glass where the origin of the breakage is up here in the upper left corner. And this is for a chemically tempered glass with a low amount of tension, so a relatively low amount of compressive stress, in other words. Now, what you can see is that as the crack propagates, the tensile energy in the interior of the glass is being released, and that is accelerating the crack tip until it reaches its terminal velocity. When it gets to that point, the crack cannot propagate any faster, and so it has to branch. It has to bifurcate or sometimes even trifurcate. So it's branching into two or sometimes even three new cracks so as to be able to release that tensile energy at a faster rate. When those new cracks form, each one of them is then going to propagate and accelerate as its tensile energy is being released until that new crack reaches its terminal velocity. And then another crack branching event will happen again. That crack tip will accelerate again as the tensile stresses are being released. And this process repeats itself over and over again. And you get this type of fractal-like patterns here. And the important thing to note is that these energies that are creating these fracture patterns are coming from energies that were stored in the glass itself. It is coming from the release of the tensile energy, which is manifesting in these tensile forces that are accelerating cracks and leading to crack branching. This is in contrast to the case of the annealed glass or the annealed laminated glass, where the patterns that you see are mostly a result of the externally applied energy from the impact. Here, it's the internal energy that is leading to these patterns. Now, this is the case of low tension. If there is a somewhat larger amount of tensile stresses, here this is a medium level of tensile stress, that means that there's a greater amount of tensile energy being released, which means a greater acceleration of the crack tip, which means that the crack tips are reaching their terminal velocities over a shorter propagation distance, which then means that the crack branching occurs after a shorter propagation distance. So as a result, this greater amount of tensile energy translates into smaller fragments when the glass is broken. In other words, a greater number of fragments because each fragment is smaller. This is something that is called frangibility or frangible fracture. Frangibility is just a word that means that the glass, when it is broken, breaks into many pieces as a result of the release of internal energy, not as the result of externally applied energy. And if you take this even further to a higher amount of tension, you see you get an even greater amount of acceleration, which means that the cracks are achieving their terminal velocities at an even shorter propagation distance, and therefore the cracks are branching earlier, forming a larger number of even smaller pieces. Now, the extreme example of this is what's called a Prince Rupert's drop. This has an enormous amount of compressive stress at the surface that is balanced by an enormous amount of tensile stresses in the interior of the glass. Prince Rupert's drops are formed by taking a small gob of glass and then dropping them into, say, cold water where they quench very rapidly, which this is like an extreme version of thermal tempering. And so if you look at the head of the Prince Rupert's drop, if you try to bang on that with a hammer, it is very difficult to break because of the enormous amounts of compressive stress at the surface. However, the weak point of the Prince Rupert's drop is the tail. So if you follow the tail all the way out here, the tail still has compressive stress in the outer part, but because the tail is so thin, it's very easy to penetrate through that and into the tensile region. And therefore, the tail is a weak point. It's very easy to break it there. And once that tensile energy starts to be released, it does so, it leads to fracture in this catastrophic fashion. It's basically an explosive fracture because there's so much stored tensile energy that is being released so quickly that's leading to enormous acceleration of the crack tip, which leads to very early branching of cracks. And the cracks, each crack is just so short and branching so quickly that ultimately it's like this goes back to dust. The pieces are just so small. So this is an example of an extreme case of frangibility because of the large amounts of tensile energy that are stored. Now, I want to point out that we can learn a lot about the conditions under which a glass broke based not just on its macroscopic fracture pattern, but also based on the microscopic markings that are on the fracture surface. So if you look at the surface of where a glass broke, look at it under a microscope, either an optical microscope or an electron microscope, you will see a lot of fracture markings. And these fracture markings can tell you a lot about the conditions under which the glass broke. This is a field of study known as fractography. It's kind of looking at broken pieces of glass or ceramics after the fact and deducing the conditions under which they originally broke. This is very useful, for example, if you want to understand if you're making glass products and you're seeing some of them break, if you want to understand why that breakage is occurring, you should look at these fracture surfaces and perform this type of fractographic analysis. Some of the markings that you'll see are this very smooth mirror region, which is the region where the crack initially propagates more slowly. This is surrounding the initial origin of the crack. This mirror region gives way to a mist region, which has more of a rougher surface as the crack propagates more rapidly and starts to approach its terminal velocity. The mist region gives way to an even rougher region known as hackle. These are deeper radial ridges that surround the mist region. And then there are also these Wallner lines, which are based on interactions between the fracture front and stress waves, including those waves that reflect off of the outer surfaces of the glass. So if you're interested in this, I definitely encourage you to pick up a book on this topic of fractography by George Quinn. It is freely available online through NIST. So you are welcome to check that out. And to summarize, we covered three different types of breakage patterns. The first is the starburst pattern that exists in annealed glass. It forms a starburst pattern because the energy is coming from an external source, because the annealed glass itself doesn't have any stored tensile energy. Then there is laminated glass. This is where you've got a polymer layer that kind of holds things together that can lead to more of a spider web type of fracture pattern, but also helps to prevent the ejection of broken glass shards. And then tempered glass, either thermally or chemically tempered glass. If there is a compressive stress at the surface, it's balanced by tensile stresses in the interior. When the crack propagates through the compressive stress region into the tensile region, that's what leads to the release of that tensile energy that accelerates the crack tips and leads to crack branching and ultimately to frangibility. And if you'd like to check out more, please check out our textbook, Fundamentals of Inorganic Glasses. And as always, if you have any questions, feel free to drop them below and I will get back to you as soon as I can. All right, thanks everyone. Hope you have a great day.